So, where we left off in class was starting to move beyond diatomic molecules and looking at larger systems like water, everyone's favorite inorganic molecule. Now, this doesn't mean that diatomics aren't worth investigating. In fact, we'll do a little bit more practice in class on diatomics like F2 and even heterodiatomics like CO and NO, because constructing their molecular orbital diagrams helps us understand their reactivity a little bit greater. So we do spend some time on diatomics, but we want to start building up to larger systems, right? When we think about chemistry, we start thinking about things that often involve a lot more than just two atoms. So molecular orbital theory needs to be applied to these much larger systems, such as water. And as I alluded to before, one way that we can do this is by treating the hydrogens as their own independent set of wave functions. And so we have this equation from our last video where we had this molecular orbital wave function. And we said that this is just the sum of these various component wave functions from each of the atoms, right? This is the linear combination of atomic orbitals theory, right? That we can take these different functions and then just combine them to get a new wave function. So what we're going to do when we look at water is we're going to take this a step further, and we're actually going to group up the hydrogens. So what does that mean? It means that we are assuming that the hydrogen orbitals themselves are not strongly interacting with each other, right? If we go up here and look at this Lewis structure, I'm implying that there's no real bond or interaction between the hydrogens in a single molecule of water. So that means that we have two possible outcomes for these orbitals. They could either be in phase or out of phase. And we're going to come back to this when we dig deeper in group theory and see how these derivations come into play. But we can say that there's essentially two orientations, right? So we're going to lump these terms together into what we're calling SALC, S-A-L-C, which stands for Symmetry, Adapted, Linear Combinations. Right, and these SALCs we're essentially going to group up these hydrogens, and we're going to say you could treat these hydrogenic orbitals, right, or these hydrogen orbitals as two different possibilities, right? So we're going to call it phi 1 and phi 2. And the first option is saying, okay, well, let's assume, right, that these hydrogen orbitals are in phase, meaning they're the same shade. And our other possibility, again, we're only working with two atoms here, so it's a little bit easier to imagine these. But our second possibility is let's assume that maybe they're out of phase. And like I said, we're going to come back and prove that these are in fact the two SALCs for water later. But for right now, we can just go with a graphical picture as we derive these molecular orbitals. So it's not saying that we're doing a lot of quantitative information right here, right? We're just doing a qualitative pass. And so these are our two options, right? So we can treat these as if they are just combinations or the possible combinations of our hydrogen orbitals. So if we want to piece together our MO diagram, what we can do is, again, we can put our hydrogens on one side, right? So now we have our two hydrogens on one side. We have our oxygen atom on the other. And so if we're going to use our ionization energy data here, again, there's this zero energy state up here. And this is the separated electron from its atom. And then we can measure these binding energies and we can try to kind of plot them out. So we have our hydrogen orbitals, right? So these are our SALCs for hydrogen. And these we're going to assume, and again, this is an assumption, we're going to assume that these are at that same ionization energy as the individual atoms themselves. Right, so negative 13.61 eV is what we have here. And again, this corresponds to the in phase and out of phase combinations of these orbitals. Now you might be saying, well, the out of phase one, that looks like it should be higher in energy, right? That might even look kind of like an anti-bonding arrangement. But we go back to our assumption, and our assumption is that these orbitals on the hydrogens are not interacting with each other in a significant manner. So that's why we are going to assume, right, and it is an assumption, that they are of nearly equivalent energy. right? So now we need to fill in our oxygen atomic orbitals. So we have our 2s orbital, right? That's way down here at minus 32.38. And then we have our p orbitals at minus 15, our 2p orbitals. So again, if we're going back to our approximations when we're thinking about molecular orbitals and these binding energies, is we're going to assume that the SALCs, right, these hydrogen orbitals, are going to predominantly bind or interact with the 2p orbitals of oxygen because they're much closer in energy, right? So we're going to assume that there's a minimal interaction with something like the 2s orbital because those those energies for these orbitals are dramatically different. So what we really care about, right, what we're really focused on right now is this region right here in the middle, right? So this is where we're going to look at how do our SALCs, right, interact with the 2p orbitals on oxygen, right? And this is the question that we're asking, right? How are these going to interact when they get close enough together? And so I kind of hinted at this a little bit in our last video where I said that there's going to be interactions with these p orbitals. So let's imagine the orientation of our three different p orbitals with these two possible SALCs and see if there's any that match up, right? So we have our axes here, so let's draw these out. So again, I have my px, py, and pz orbitals. So I'm going to start with my px orbital. So if we're following my axes here, right, if I have px, right, and so it looks kind of like this. And I have two different SALCs. Remember, we had our in phase and out of phase. And so I'm curious, right, which of these, if they mix, if they interact, right, if I draw my atomic orbital for my oxygen along with my SALCs, these s orbitals on my hydrogens, which ones could I have a productive bonding interaction for? And so it turns out that if we have, so I labeled these before as phi1 and phi2. So if we imagine that I actually have phi2 plus my px orbital, right? What that would look like is I have my kind of exaggerated axes here. So this is that phi2. Here's my px. And I can see that in general, my phasing lines up, right? If I'm imagining now that my oxygen is in fact interacting with my hydrogens, I would say that this could now form a bonding-like orbital and actually an anti-bonding orbital. So as we talked about previously, right, there can be constructive interference and destructive interference whenever we construct a molecular orbital. And so the constructive interference piece, right, we would essentially have a big lobe that's unshaded and a big lobe that is shaded. And this is just roughly this picture of trying to combine together the px orbital with this phi2 set of ligand orbitals, right? Ligand in this case, in quotes, being our hydrogen atoms. Similarly, if they were out of phase, right, if we had a destructive interference, right, they would essentially be pushing, the way I think of it is like they're pushing against each other, right? We've now increased the number of nodes in this molecular orbital, which means we would have a greater energy, right? So here I can see that I actually have 3 different nodes in this molecular orbital, right, which is separating out the electron density for this molecular orbital. Whereas in my bonding configuration, there's only 1 node, right? And so now I can see that for my px orbital, right, this can interact with one of these SALCs to create what looks like a bonding interaction and an anti-bonding interaction. So let's see what happens next when we look at py. So again, we're going to have the same set of SALCs that we're evaluating here. All right, so let's copy these so we can move them over with us. right? So here's our same set of Salks that we're working with, only now we're going to be looking at PY. So if we're looking at PY here, right, it's pointed straight up and straight down. In our understanding of our p orbitals, right, we understand that the two different lobes are shaded different colors, right, for the phasing. So this is that py orbital that we're evaluating. And again, this py orbital is centered on the oxygen, right? So how could we draw this picture and see if there's any type of interaction between our oxygen atomic orbitals and these Salks that we are given for our hydrogen orbitals? So let's imagine, right, that we are going to be combining these. So I have my py orbital on the oxygen, right, that looks kind of like this. So which Salk would we combine, or if we had to choose one of our Salks, which one would actually interact strongly with this py orbital? Well, it actually turns out that it's phi1, our in-phase orbital. We can see here that when these are aligned, that essentially that bottom lobe of that p orbital is lined up really well with our hydrogen s orbitals. So again, this means that we can get a nice bonding and antibonding interaction. I said that in reverse, right? We would put our lower energy case as our constructive interference, meaning bonding, and destructive interference would be our antibonding up top, right? And so if we're going to draw these pictures out, you could just draw them as drawing in the atomic orbitals. That would be fine. But we could also imagine that this would now look for our constructive interference section. It kind of looks like our two s orbitals combined in with the p orbital of our oxygen. So we're left with this out of phase lobe up top, but largely our p orbital has mixed with both of those hydrogen s orbitals. The constructive interference is drawn below. So our destructive interference, right, would show this p orbital and our our hydrogens that are not in the same phase as our p orbital. So again, we can see in this top case, right, that there's kind of a conical node, or not even a conical node here, but there's a node separating that p orbital. Whereas here, again, in our antibonding configuration, there's actually three different nodes that we're looking at here. So we have an antibonding and a bonding configuration here for our py orbital. Now, the next one is one that throws people for a loop, because our last case that we're going to look at is, again, what's happening to our px orbital. So let's take this one again. All right, let's look now and see what happens to our px orbital. So px is kind of sticking out of the drawing surface here. Right, so it's sticking kind of out of the plane of the paper. And what I can see when I start to line these up, right, if I were to try to draw out my px orbital sticking out of the drawing surface here, and my hydrogen orbitals, what I see is that there's actually, that the hydrogen orbitals themselves, or the hydrogen atoms themselves, I should say, align perfectly with what we call a nodal plane of that p orbital, right? So the hydrogens, right, or I should say the hydrogen s orbitals, lie in the nodal plane of my pz orbital as drawn. So let me make sure that I have this labeled correctly. Obviously, my brain is not working today. So this is my pz orbital. I did py and px. Good. Okay. So this is my pz orbital, which is kind of sticking out of the drawing surface here. And I can see that inside this nodal plane of this pz orbital is the plane that contains my hydrogen s orbitals. So what does this mean? It means that there's no bonding interaction that can occur with my pz, right? Whether these are in phase or out of phase, they are perfectly lined up with both lobes of my p orbital. And so there's actually no interaction that occurs with my pz. And this is something that is kind of confusing to a lot of people when they first see it, because what I'm saying here is that essentially there's a molecular orbital on water that looks just like a p orbital from the oxygen, right? So let's look at this and let's draw out some of these pictures. So here we have that kind of blank diagram that we started with from a few slides ago, where we were looking at this electron configuration for oxygen and these combinations of my hydrogen atoms. What I said is we're going to assume that there's minimal, if any, right, interaction between the s orbital of oxygen and my hydrogen orbitals because they have dramatically different ionization energies. In reality, there's a very small interaction here. So I'll kind of add that as a little caveat. So if you look this up, you'll see that there is a small interaction that occurs. But again, it is relatively minor compared to the interaction with the p orbitals. And so we're just going to call these, right, with the capital phi here for our, or psi, sorry, for our molecular orbitals. So we'll call this psi1. And again, psi1 largely looks like the 2s orbital on oxygen. So let's look and see again what happens to x, y, and z based upon the pictures that we had drawn earlier. So what we saw was that X can form both a bonding and anti-bonding orbital, right, or sets of molecular orbitals. So let's draw these in. So this is my X that's along my axes here. So I'm kind of exaggerating these so they're easier to see. Right, and so this was my px orbital that was with my out of phase SALC. Right, so this is a bonding orbital. I'm going to call this psi2. Right, similarly, y, which we're going to call psi3. Right, my py orbital here. So this is essentially the lower lobe of that p orbital is the same phase as my SALCs, right, my hydrogens. I said that there's going to be, for pz, essentially no interaction. So psi4 is actually just the pz orbital on my oxygen. So if we go back and think about terminology from our last video, I might call this a non-bonding orbital. The other way to think about this is a molecular orbital where the coefficient is 1 on my pz atomic orbital, right? So that's some ways we can think about this. I also have two anti-bonding orbitals that came from my SALCs interacting correspondingly with py and px. So the first of these anti-bonding interactions would again come from where my phase of the lower part of my p orbital is out of phase with the SALC. And this top case here, so that was psi5, which again is an anti-bonding, which we denote with a little star. And up here is psi6, which is also anti-bonding. Came from where my px orbital had destructive interference with the corresponding SALC. Right, so that would be psi6 up here. So let's look and see where my electrons would fall for water. Right, so hydrogen, each of these had one electron. Hydrogens have one electron, so if I have two hydrogen atoms, then it makes sense to say that they bring two electrons to the party. Right, my valence orbital for oxygen would have 6 electrons. Right, so it would have a configuration that would look like this with my 6 electrons. So I can go ahead and start filling these in on my, my molecular orbital diagram. 1, 2, 3, 4, 5, 6, 7, 8. So how do we interpret this, right? What does this whole diagram mean? Well, one, we were able to construct this graphically using our orbital pictures, right? But two, how does this relate to the bond order? Well, what I can see here is that I have psi 1, 2, 3, 4, 5, and 6, and I can classify these, right, as either being bonding, anti-bonding, or quote-unquote non-bonding, or a localized orbital. And so what I see here is that I have one lone pair, or one set of electrons, that's in a non-bonding orbital. Right, and again, non-bonding just means it looks like the atomic orbital, right? The coefficient is 1 from the atomic orbital down here. Secondly, I have another set of electrons that also looks like it's a non-bonding electron pair, right? NBE. And if I look at my Lewis structure for oxygen, sure enough, it definitely looks like I have two lone pairs on my oxygen atom that we would classify as non-bonding. So our molecular orbital picture currently matches up with our Lewis structure. Our Lewis structure also contains two sets of bonding electrons, right? We have two filled bonding orbitals. And sure enough, if I look at my picture up here, I draw this out as if I have two bonds, right, between my oxygen and my hydrogens. So it sure looks like the bond order here should be 2. And in fact, I do see two single bonds. So what are we losing here? Well, our picture, our Lewis structure picture, doesn't really convey the nature of these bonds. It describes them as two separate bonds between oxygens and hydrogens. When in reality, what we can see from our molecular orbital picture is that these bonds are spread out, the electrons for these bonds are spread out between both hydrogens and the oxygen. Similarly, our Lewis structure makes it look like our lone pairs are equivalent, when in reality, one of them is buried much deeper on the 2s orbital, right? Much less reactive, and one of them is much more accessible as essentially our PZ orbital that came from an oxygen atom. And in fact, this matches our photoelectron spectra for water in the gas phase. When we gather a photoelectron spectra, what we see matches our MO picture drawn here, that we have a set of electrons that almost exactly matches the energy of a free oxygen atom, right? And that corresponds to this non-bonding electron pair that originated from that PZ orbital on the oxygen. So now what we can start to do is think about these as like a graphical way of approaching and constructing molecular orbitals. So if we are given these calcs, if we are given these pictures, we want to start being able to connect and draw out potential molecular orbital diagrams. We're going to start exploring this for transition metal complexes later this week. And what we're going to do in the early part of next week is talk about how do we generate, using group theory, these particular pictures, these calcs. So for right now, you're given the calcs. In the future, we're going to talk about how we derive these potential combinations of our ligand orbitals. And again, I'm kind of leading with that use of the word ligand by saying we're treating this as a central atom and then things that are attached to that central atom. Okay, so I will see you in class where we will get some more practice with diatomic molecular orbitals, as well as using some of these calcs to generate molecular orbital diagrams for more complex pictures. Thank you.